Hey loyal fans! In this video I explain special relativity, a cornerstone of modern science and a field that affects virtually all other fields. It's not an exaggeration to say relativity is a kind of celestial clockwork that explains how much of the world works. Some parts of relativity shock the unprepared. In fact, we accepted relativity only because our experiments forced us to accept what nature was trying to tell us. For those keeping score, this video explains special relativity, which covers everything except gravitation and curved spacetime. I'll explain general relativity in a future video. Relativity describes, and explains, much of reality. Even though they're surprising, most relativity ideas are easy to understand, and the more exotic ones are fun to learn. Relativity explains how and why the sun can burn for billions of years, and why fusion power will solve our energy problems. And relativity knowledge is part of every educated person's intellectual toolkit. By the end of this video, you will know why 3 dimensions aren't enough to explain reality, and how it is that a tiny mass can possess enormous energy. I start by explaining what came before relativity, how modern relativity theory came to be, and why relativity ideas are essential to sorting out reality. So hey, let's get started. During the Enlightenment, in the 17th century, people began to question ideas that until then had been a matter of belief, not evidence. This was the time of Galileo and his telescope, of Isaac Newton supposedly being bonked by an apple while thinking about gravity. This needs a little historical context. Until the Enlightenment, people's understanding of the world sprang from belief, not evidence. Those who tried to inject evidence into the process were either killed outright, as with Giordano Bruno burned at the stake in 1600, or threatened with torture and subjected to lifetime house arrest, as with Galileo a few decades later. Newton believed time was universal, passing at the same rate everywhere. Based on what was known, this was a reasonable assumption. Even though Newton pictured an absolute conception of space, he had begun to think about relative frames of reference within space. Galileo Galilei tried to measure light speed with 2 lanterns on separate hilltops. It was a bit crude. Galileo concluded that light speed was either infinitely fast or too fast for his method. Later on, astronomer Ole Rømer noticed that Io, one of Jupiter's moons, periodically changed the timing of its orbit based on its changing distance to Jupiter. Rømer realized the change might be caused by a finite speed of light. He then calculated a value surprisingly close to the modern one. Once people accepted that light had a finite speed, they began to ask themselves what medium conveyed light from place to place. We knew that air carried sound from place to place, and without air there would be no sound. So, what carried light? After much time and study, early scientists crafted the idea of a luminiferous ether that filled all of space and carried light waves, much like air carries sound waves. By the 19th century, science had advanced to the point that many ideas which until then had been assumed to be true were instead subjected to test. People realized that if luminiferous ether filled all of space, that's the blue fog in this video, we should be able to detect it. Because the Earth is speeding along its orbit through space, with the right equipment, we might be able to detect our speed with respect to the ether. In 1887, scientists Albert Michelson and Edward Morley created something called an interferometer, a device that should have been able to measure our speed through the ether. A little digression. This is my model interferometer, designed in a very nice, free, open-source graphics program called Blender. Even though my model has the same purpose as the classic design, it's actually much better than what was built for the now famous experiment. This is how such an interferometer would be built in modern times, with lasers and modern optics, none of which were available in 1887. See how my model's stone turntable can turn freely? This is because it's floating in a pool of mercury. Some might wonder how a heavy disk of stone can float like a boat in a pool of mercury. Why doesn't it sink? As it happens, because mercury is super dense, denser than stone, the stone turntable floats in a little mercury ocean. The original Michelson-Morley Interferometer used the same method. By the way, don't try to build a real-world model like this. Mercury is very dangerous. Anyway, back in 1887, the Michelson-Morley experiment failed to detect a luminiferous ether. Remember that in science, a failed experiment is just as important as a successful one, assuming the experiment is carried out properly. After this failure, and because of the importance of ether theory, people carried out many similar experiments, all with negative results. Some tried to explain the failure. Maybe the Earth carried an environment of stationary ether along with it, as in this animation. So the experiment was unable to detect Earth's speed through the ether. This experimental phase, now called saving the ether, lasted from 1887 until 1905. During this time, Michelson made a now famous remark about the state of science, that basically it was finished, only needing a few adjustments to complete our understanding of nature. He couldn't have been more wrong. In 1905, while working as a patent clerk in Bern, Switzerland, Albert Einstein published a paper that, although it contained original ideas, built on the work of others, including James Clerk Maxwell on electromagnetism and Hendrik Lorentz on the geometry of space and time. In his 1905 paper, Einstein moved past older theories, establishing, among other things, that the speed of light was the same for all observers, regardless of their relative motion. This revolutionary idea required that space and time change to accommodate light's constant speed. The equations in Einstein's paper were internally consistent and satisfied physical principles, but they were open to an interpretation Einstein missed. Hermann Minkowski, Einstein's former math teacher, realized Einstein's equations could describe 3 space dimensions and 1 time dimension, an idea that Minkowski called Spacetime. Minkowski developed this idea independently, later saying, "Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." This space-time interpretation of Einstein's equations came to be preferred over Einstein's original formulation. About this change, Einstein later said, with humorous intent, "Since the mathematicians have invaded the theory of relativity, I do not understand it myself anymore." Einstein eventually adopted the space-time idea as a foundation for his later work. By the way, Einstein's theory did away with the need for a luminiferous ether. Light speed and a separate time dimension are bound together in a way that makes an ether unnecessary. Let me take a few minutes to explain a key idea having to do with the speed of light. Because spacetime has 4 dimensions, and because most people can't directly visualize more than 3, my graph has just 2, the horizontal axis, which represents 3 space dimensions rolled into 1, and the vertical dimension, which is time. Please pay particular attention to this graph, which I've designed to simplify as much as possible the relationship between space, the horizontal axis, and time, the vertical axis. The controlling factor in this graph, just as in reality, is the constant speed of light, represented by the yellow fixed-length diagonal line. This graph is meant to show something important about space and time, which is that space velocity exists at the expense of time velocity. The diagonal yellow line shows the relationship between space and time. As we increase our speed through space, the horizontal axis, we must proportionally decrease our speed through time, the vertical axis. Massive objects cannot move through space at the speed of light, but massless particles can. Photons, which are massless particles of light, travel at the speed of light. This graph shows reality from the perspective of a photon, which, because it moves at the speed of light, does not experience time. A photon's life, from creation to absorption, requires 0 time, even if it travels across the universe. By contrast, at zero space velocity, time resumes its normal pace, which, wait for it, is the speed of light. Try to remember this point. Ordinary time passes at the speed of light, taking the entire universe along with it. A few months after Einstein published his relativity paper, he realized what the speed of time might mean for all the mass in the universe. When a massive object gains speed, its energy increases as the square of that speed. That's called kinetic energy. This means if you double your car's speed, you need 4 times more distance to stop. Einstein realized this rule applied to all masses in the universe, which race through time at the speed of light. Einstein derived a version of the kinetic energy equation that applies to the speed of light. Notice that Einstein's most famous equation is derived from the everyday kinetic energy equation. They're part of a continuum. But the amount of energy implied by his new equation surprised even Einstein, such that the title of his paper included a question mark. The new mass-energy theory resolves some scientific mysteries. In earlier times, physicists believed the sun released energy through simple gravitational collapse, which would have limited the sun's lifetime to about 20 million years. But geologists suspected the Earth was much older than that. In fact, some lines of evidence suggested the Earth was many billions of years old. Charles Darwin's theory of evolution, first published in 1858, had plenty of supporting observational evidence, but Darwin believed advanced organisms like humans could not evolve in a mere 20 million years. More time was required. This time horizon was a legitimate objection to Darwin's theory of natural selection, and Darwin knew it. Einstein's energy equation resolved these issues. Scientists now understand how nuclear fusion works, which gives the sun a lifetime of 10 billion years. This example also demonstrates how one scientific discovery may support another in an unrelated field. Einstein's mass-energy theory is validated by the requirements of evolution, and Darwin's theory of natural selection is validated by relativity's mass-energy equivalence. Without nuclear fusion in stars, advanced life forms would not be possible. Think about this. Without Einstein's mass-energy equivalence theory, stars would collapse under gravity and go cold, without giving life a fighting chance. Instead, a star collapses under gravity only until internal pressures and temperatures become high enough to ignite nuclear fusion. As a star collapses, gravity creates an inward force which heats and compresses atoms. The atoms begin to fuse together and release energy, which creates a balancing outward force. This balance between the inward force of gravity and the outward force of fusion stabilizes the star for billions of years. This long stellar lifetime is essential to the evolution of advanced life forms. If you take nothing else from this video, please remember this. Dust clouds collapse under gravity. Then, instead of winking out after a few million years, they begin nuclear fusion. This begins a lifetime, measured in billions of years, of steady energy output. Stars become trustworthy nuclear lanterns that make life possible, make us possible. Apart from nuclear fusion, relativity has more practical effects. It means most observations depend on a particular frame of reference, and in most cases, there are no preferred frames of reference. All are equally valid. Here's a classic example from an early book written by Einstein. Let's say there are 2 observers, one standing adjacent to a railroad track and one riding in a passing train. At the moment the 2 observers are next to each other, 2 lightning bolts strike opposite ends of the train. For this example to work, to be visible, let's pretend that light has a much slower velocity than it actually does. As time passes, as the train continues on its way, the lightning flashes reach the observer's location near the middle of the train. The trackside observer, that's observer A, sees the flashes at the same time, so, aware that he is stationary, concludes that the flashes were simultaneous. The train observer, observer B, sees the forward flash first, but by taking his forward motion into account, agrees that the flashes were simultaneous. Conclusion: the flashes were simultaneous. Now let's change perspective. Let's make the train the stationary frame of reference and make the world the moving frame. In this perspective, the train observer is stationary and the trackside observer is moving toward the left. As before, when the observers are next to each other, lightning strikes opposite ends of the train. The trackside observer sees the flashes at the same time, but by taking his rearward motion into account, concludes the forward flash happened first. The train observer observes the forward flash first, so, aware that he is stationary, agrees that the forward flash happened first. Conclusion: the forward flash happened first. In both cases, the observers agree, but they come to different conclusions based on the choice of perspective. So which perspective is correct? Were the flashes simultaneous or not? The answer is, there's no preferred answer. Both perspectives are equally valid. This means we cannot legitimately say that two events separated in space happened in any particular order. This is called the relativity of simultaneity. Even in relativity, some rules are never broken. Two of these rules are A, an event cannot happen before its cause, and B, an effect must be linked to its cause by a speed less than that of light. Here's a light cone diagram in 3D. The center of the light cones is the present place and time, or here and now. The light cones are meant to show how the past, present, and future are connected or not connected, as the case may be. The surfaces of the cones represent the speed of light. The surfaces are event barriers, which means that any event outside the past and future cones would have to exceed the speed of light to either get to the present place and time or come from the present place and time. The light cone is based on a simple idea. If an event is located within the past cone, it can influence events in the present without exceeding the speed of light, otherwise it cannot. In the same way, events inside the future cone may have been caused by the present, otherwise not. Now stretch your mind a bit and imagine that every point in space and time, past and future, has its own light cone. In special relativity, nearly everything is relative, not just events separated in space. By relative, I mean reliant on a particular point of view, a perspective. Among these are time, all relative; positions in space dimensions, all relative; velocities, all relative. There's one exception. In special relativity, accelerations are absolute. I'm clarifying this because in general relativity, not this video's topic, and because of the effect of gravity, accelerations are relative. In special relativity, accelerations are absolute because they result from an object's interaction with all the rest of the matter in the universe, an effect Einstein called Mach's principle after Ernst Mach, who first discussed it. In this video, I spin a cylindrical container and see the liquid take a parabolic shape because the cup's interior wall applies a centripetal force to the liquid as it spins. This is an example of Mach's principle. The liquid is being accelerated with respect to the rest of the matter in the universe. But in the reverse case, if the cup is stationary and the room spins around, the outcome won't be the same because the liquid is not accelerated with respect to the rest of the universe. Remember about this second animation that I'm only spinning the room around, not the entire universe. This comparison shows that, at least in special relativity, accelerations are absolute. Well, I think that's enough information to pack into a single video. Again, please remember this video's key point, the essential connection between relativity and earthly life, the modern-day discovery that without nuclear fusion and the reliable energy of stars, humans wouldn't have evolved. This was always true, but we needed clever, resourceful people to explain it to us. Thanks for watching. Please like and subscribe, be well, and grant me 30 more seconds of your time.